Good afternoon. I hope this video is going to be very helpful for you, so we'll get started. This is day 2 of thinking about derivatives as functions. So derivatives as functions. So the assumption is that you have already started to think about derivatives as functions using the POGL, and now I want you to use that POGL to start really understanding some big ideas. So please take out your POGL from last class. You should have done problem numbers 1 through 6, and if you did not do number 1 through 6, then you're going to have to get as much as you can from what you've done. What I'd like you to quickly do is compare what you said for number 6 with a neighbor, and just consider what kind of generalizations can you say about the comparison that you had on the first page. So on the top page you colored, so you had some function that you were thinking about, and then we had some derivative function that we were considering, and that was down below, and we thought about different things, and yet we shaded the top one color. And it turns out that when we shade them, they end up being shaded approximately the same thing. So when it's increasing, and when it's decreasing down below. So hopefully you see that those colors all line up. But my big question is, when you're looking at yours, what's the difference? What is happening up on this original graph, and how does that compare with the slope down below, the slope graph from down below? What generalizations could we make about this upper graph based on the information that we know from this bottom lower graph? So that's really what we're thinking about today. As you're doing it, please pause the video and spend about 5 minutes coming up with written statements about generalizations that you have as a whole class. So we should have a whole class answer. And then maybe think about, as you're going, if you finish early, which points have a slope of 0? In other words, where is g prime of x, the slope of the derivative, where's the slope of the derivative 0 in the original function? So those are 2 things to think about. Please pause the video, as a group come up with some understandings, and then we'll move on. All right, so I just want to highlight our learning target for today. We're really going to be focusing on understanding the sign, so positive or negative, understanding the sign of the derivative, and that it has a graphical meaning for a function. So you're going to be successful today if you can identify where the function is increasing or decreasing by looking at the derivative function. And then, by the end of class, you should start to be able to match graphs of functions with graphs of their derivatives just by looking at small intervals and approximating the slope. So, what that might mean is you might be able to say, oh, this is the graph of the function. I know that the derivative is the slope, so the slope is down here, so I'm going to say it's very negative, and then it's a little bit less negative, so it's less negative. It's 0, it's positive, and then being able to identify, oh, the derivative graph, the f prime graph is this when this original function is f. So that's what you should be able to do by the end of class for a bunch of different functions. We'll continue working on that because it's actually quite challenging to do. So I'm going to have you pause the video and return the quiz. We're going to go over the problems together. So pause the video and please distribute the quizzes. All right, at this point, you should have your quiz. Please go over each problem together. We're going to do that in just a second. But I strongly recommend that you do quiz corrections. You don't have to do those quiz corrections, but it's going to be really important as you retake things. And if you haven't done it the first time or you haven't gone over it, the first time on your own, then what's really the point of retaking it? So please do quiz corrections. I think they're smart. We're about to go over each of the problems, and these examples are posted to my website. So you can always watch this video on my website later. So this is what your quiz looks like. I'm going to here zoom in so that everybody can see it. A derivative is a limit as a difference quotient. So I showed you this, and I gave you the derivative function. So we learned about the limit definition of the derivative, but what's equally as important is knowing where it comes from and what information it tells us. So I was looking for a few key things. I was looking for you to describe where this formula comes from. So if you were doing this, describing where the formula comes from, I was expecting to see things on your paper like, it's from the average rate of change. It's coming from that formula. Or I was looking for you to say it's coming from the slope formula. Or I was looking for things even that were like it's coming from the secant line formula. Because those are things we've talked about. Another piece that I also needed was what information does it tell us about the function. So you needed to answer both parts in order to get a 4. And to answer the blue information, what I was looking for is it tells us the instant rate of change, instantaneous rate of change at a point. So not everywhere, but just at a specific point. Or the derivative, but I think that is not quite enough. Because I think that this tells you a lot more than just derivative, and that doesn't really show your understanding of what a derivative is. So instantaneous rate of change, the slope at a point, all of these things, all of these things could be what you wrote on your paper. It doesn't have to be all of them, but at least some of them is what I was expecting to see from you. All right, we're going to move down to the bottom part. Calculate the derivative of the function y equals 7x minus 18 at the point x equals 2 using the limit definition of the derivative. So I was looking for you to use this limit definition of the derivative. So let's start there. The limit as h approaches 0 of f of x plus h minus f of x all over x plus h minus x. And so we knew that the x value was 2, so we're going to replace all of these x's with 2 because the x was 2 in the original problem. So 2 plus h minus f of 2 over 2 plus h minus 2. Okay? And that's equivalent when we substitute it into the function limit as h approaches 0 of 7, where the x is, we got 2 plus h minus 18. Here's where most people messed up. It's subtracting all of this stuff. So I'm subtracting 7 times 2 minus 18 because that then has to distribute. And then we're all over h because the 2's cancel out up here. So distributing, we're going to keep going. So the limit as h approaches 0 of 2 times 7, so 14 plus 7h minus 18. And then I'm distributing. 7 times 2 is 14, so minus 14 plus 18, all still over h. When we start canceling things out, 14 cancels out with negative 14, 18 cancels out with negative 18, and I'm left with the limit as h approaches 0 of 7h over h. H on numerator and denominator cancel out, and when I evaluate that limit as h approaches 0, we get 7. So your answer is 7, and that kind of makes sense because if I'm graphing a linear function with a y-intercept at negative 18, it's just a line with a slope of 7, and any point on this line, the slope is going to be 7. The slope at that point all the way up and down this line forever and ever is always 7 because the slope of the line is 7. So that's how you do that. All right, we're going to move on real quick. This is a problem that requires us to really analyze some information. So we're thinking about this group that's throwing a basketball off the top of a building. The building is 533 feet. They're trying to break a world record. By the time it reaches the ground, it is going to hit the rim of the basketball hoop, and that's modeled by this function, where t is the seconds, and f of t measures the ball height in the metric of feet. So if we're using the equation to determine the ball's speed the moment before it hits the rim, we're really doing a derivative. We're using a derivative to calculate the instant speed at that point. So we're calculating the speed at the slope at t equals 5.7. So the limit as h approaches 0 of f of 5.7 plus h minus f of 5.7 all over h. I think we, at this point, know that the denominator is only h when they cancel out. So if I'm going to substitute this in, this is equivalent to the limit as h approaches 0 of negative 16 times 5.7 plus h squared plus 533 minus all of that stuff. So negative 16 times 5.7 squared plus 533 all over h. And this is a lot of algebra on the numerator. So I'll just quickly do it. So negative 16 times 5.7 plus h times 5.7 plus h plus 533. And when I do the stuff in the parentheses, I get 13.16. So I've already simplified all of that right there. So when I simplify it, that's what it becomes. All of that's over h. I'm just going to squeeze this up. This is the limit as h approaches 0 of negative 16 times 5.7 times 5.7 is 32.49. This h times 5.7 and this 5.7 times h ends up being 11.4 h, and then h times h is obviously h squared. All of that in parentheses plus 533 minus that 13.16, all of that over h. Now I need to distribute this 16 to everybody. So the limit as h approaches 0 of negative 519.84 minus 182.4h minus 16h squared plus 533 minus 13.16. All of that over h. It's going to get really simple here because when you reduce all of these numbers, when you reduce all of these number parts, they all end up actually going away. So all of this cancels out with all of the numbers there, and we're left with the limit as h approaches 0 of negative 182h minus 16h squared all over h. I'm going to factor out the numerator, the limit, as h approaches 0 of h times, negative, I didn't copy that, 182.4, my bad. Negative 182.4 plus, that's a minus 16h all over h. Almost done here because these, it's times, they cancel out, and the limit as h approaches 0 of negative 182 0.4 minus 16h. As h approaches 0, this term goes away, and it's negative 182.4 feet per second. So that's the units that we want. If you didn't put them, that's okay. You should at least know that it is a negative slope and speed is a negative speed because there's a downward slope. All right, we're going to move on to the next piece of class. So go ahead and put this away. We're going to retake this standard a little bit later in the semester, probably next week or the week after. But I haven't said anything, so I'll tell you before you get back. It's not anytime super soon. All right, so you've seen this before, and hopefully you've been able to do all of the things down here, filling this in. We did this last class. In your groups, I want you to focus on doing problems 7 through 9 in your groups. We're going to come back together, and I want us to think about number 10 together. So maybe you can come up with something on your own. You're going to share it with a partner and see if there's a bunch of different examples. And then as a whole class, I want you to do number 11. We'll do 11 through 13 together. We probably will not have time for 14 through 15, but just thought I should let you know that that's what we'll do next time, and that finishes up this packet and the understanding that happens with this POGL. So when we're looking at this, number 7 through 9, I'll just go ahead and get you started. What the first thing I really want you to do is mark each of the points where the derivative equals 0. So remember, if we're thinking about derivatives, there's a negative slope, there's a zero slope. So on this, I would mark 0 slope. There is a positive slope, positive slope, positive, 0 slope again. I'm going to put another point for where the derivative equals 0. And then part B is a little bit confusing. It says label the intervals as appropriate. I'm looking for between wherever this comes from and here, is this derivative of this function greater than 0? Then I'm going to put a positive. Or is it less than 0? I'm going to put a negative. So go ahead and pause the video and get some time. We'll go over it really quickly. Please pause the video now. All right, welcome back. You should have done this problem. I'm just going to go over the answers really quickly. So anytime I have a change in direction is where I'm going to have a slope. Now this point right here, the one that I just drew, the last point, this actually does have a 0 slope because it flattens out. Even though it doesn't change directions, it still has a 0 slope up here and all the way down there. So in total, there should be 5 intervals where the slope is positive. Where you have a positive marking, meaning that it's increasing. So I'm going to do every place where it's increasing. I see one place where it's increasing in this interval, it's increasing, it's also increasing in this interval, and finally it's increasing all the way over here. The decreasing intervals are the first one between almost every other thing that is going down at this point. All right, if most people, just so you know, match each statement to its conclusion. So you're going to actually match all of these to the problems over there. So all of these go to something over there, and we'll go over them in a half a second. I'm going to erase them while you're getting started. So pause the video if you haven't tried number 9 yet, and just resume when you're ready to go. All right, if I'm thinking about number 9, if f prime is positive, meaning the slope of the derivative is positive, then the function is increasing. Yeah, the function is increasing. If the function is positive, if I look up ahead, if it's positive, there's no maximums where it's positive. There maybe at the ends of them, there might be but no, it's not for positive. So where might there be a local maximum or minimum? Oh, that's if the slope is 0. So B. A car modeled by F is speeding up. So if it's speeding up, that means there's a positive velocity, which that means that the slope is positive. So there. The function F is decreasing. Well, that makes sense when the function F is decreasing. That's happening all the way up here. So decreasing slopes. So that goes to a negative derivative. A car modeled by the function F has no velocity. This means it's not changing going forward or backwards. That's speed is 0, derivative is 0. Okay, so E goes down here. All right, we're going to move on to the next part. Please take a moment to make sure that you've done number 10, and just know that the derivative is 0, and that when g is a, at a, and when we're not at a, that means x is not equal to a, then the derivative is positive. So everywhere at a is, everywhere other than a, it's positive, but at a, the slope of the derivative is 0. So go ahead and pause, make sure that you compare some ideas, and I'll show you a few examples that might come up. Right, hopefully at this point you have done this problem. Here are a few examples. One student did this in my other class. So it's increasing everywhere, but the derivative at a is 0. So that's one example. I'm going to delete this and show you a second example. Some kid did the same thing, but they did it a little bit higher up. So at a, the slope is 0. It doesn't matter where it is up and down, so long as the slope is 0. Okay, at a. Here's another example of something that someone did. Is they did a straight line at a. They did a curve up. So at a. Oh, that's a little bit off. I'll fix that. So it's still increasing up to a, and then at a, it's flat, and then goes off. So it's a different example, but it looks like maybe right at that point it's flat. So those are some ideas that other people have done. I told you we were going to do number 11 together. So let's take a look. So if f prime is greater than 0 on an interval, then f is, well, it's got to be increasing on that interval because the derivative is positive. If f prime of x is less than 0 on the interval f, then it's decreasing on that interval. So we can learn a lot about a function by looking at its derivative. If it's increasing, the function itself is increasing if the slope is bigger than 0, and decreasing when it's less than 0. All right, on your way out of class, this is one of the last things. I want you to try, and if you use your hand, I think using your hand is very useful here in thinking about, you can show with your hand that it's increasing and it's very, very steep. So let's do letter A together. If I'm looking at this, we're going to make some generalizations about how these functions relate to their derivative. But if I put my hand right there, if my point is right there, my hand is going to be very steep. And so it's going to be steep in a positive direction. So I'm going to go down here and say it's steep in a positive direction. So the derivative is positive. And then as I move over, my hand, if I'm drawing a slope, is getting closer, it's getting less steep. So as I move over, I'm going to say it's still positive, my slope is still positive, but it's not as steep of a positive line. And then, as I get closer and closer to, I did those points, as I get closer and closer to 0, it's going to get close, it's still positive, but it's less steep. And then at 0, it looks like there's a 0 slope. And then as I go over, it gets more and more, my slope gets increasing again. So it's increasing again. And again, it's more steep at that point. So it's steeper and steeper and steeper. It's steeper and steeper. And it looks like I can estimate what's going to happen for all of those points. So please take a moment for each of these. It's really helpful to use your hand to draw the slopes as you go through this curve to measure down below. If you finish this early, I would like you to go to number 13, but that should take us mostly to the end of class. Hopefully you've had plenty of time to practice. I strongly recommend there's some opportunities to go back to other portions of this activity to really deepen your understanding. We're gonna work through some of the other problems when we come back, particularly 14. So maybe try number 13. I think 13 is a great way to check your work if you've already done everything else. We want to know if there's a pattern between graphs and their derivatives, and hopefully you can match other graphs with their derivatives, because I think it's quite interesting. We're going to do 14 and 15 next time in class, just to remind ourselves. Thanks, and I will see you next class. I hope I'm not absent anymore this semester, because I've gone quite enough. Thanks, and I hope you have a great rest of your day. See you on Monday.